Okay, in this video we're going to do 2.2, 2.3, and 2.4. I'm going to try to be quicker, but in the last section we learned that in 2.1 we learned that arithmetic behaves like linear and a geometric behave like exponential. Okay, so basically what this is saying is these things act very similar. So in this case, the n's are the inputs and the a of n's. And these are integers, which means that you could put like 0 in, 1 in, 2 in, 3 in. And if it's an arithmetic, let's say when n is 0, a of 0 equals 2. So that'd be like a 2 right here. And let's say when n is 1, a of 1 is, let's say, 3. So then 1, that'd be like 3. When n is 2, a of 2 is 4. So 2 and 4. Now you just can't connect these dots because that's what the sequence is. The sequence, well, technically the sequence is whatever the equation is that you put in the n in to get the output. But these are called the terms. Those are the terms of the sequence. They're the outputs. You could see they each go up by 1, so that's why it's arithmetic. Where a linear function, this is what you're used to. You're used to mx plus b, where in this case, it's the same sort of idea, but these are the x's and these are the y's. So in this equation over here, it'd be like y equals x plus 2. That's the thing, right? That we did, because when x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. But in this case, you're allowed to draw lines through it because these inputs could be decimals also. And in that case, your outputs would be decimals. If you put in, like, say you put 1.5 in here, you're going to end up with a decimal as the y. So that's kind of an idea of what's going on here. Now, geometric is an exponential. So exponential kind of could go either two different ways. They kind of go real slow and then they get really, really, really fast. So that's a geometric sequence. And then a geometric, an exponential function would be like the same thing, just with lines. It'd be a curved line. It almost looks like a parabola, but it's not a parabola because it doesn't do that part over there. And an exponential is going to start growing faster. It'll be real slow, and then it gets really, really fast. So that'd be these things over here. Another thing that I want you to realize is this g of k, this is an output, and this k is the input for that output. That's like a little trick that you could use when you're doing these things. And just go ahead and read over those notes, and we'll do a couple examples, and these examples are going to be similar to something we did in 2.1. Okay, to determine if it's linear or exponential, you just have to see, is it going up by the same amount or down by the same amount? So just make sure these are equal distance too. So those are going up by 3, and these are going down by -2, down by -2, down by -2, down by -2. So since they're all going down the same amount, that would be linear. Okay, we're good on here. They're all going up by 1. Okay, that's going up 1, that's going up 3, that's going up 5, this is going up 7. So it's not linear. Now if you notice from the unit 1, if you get these subtractions, these subtractions, these subtractions real quick, you'd know that this is a quadratic. Now they didn't ask us for quadratic, but they said linear or exponential. This is neither. The way you test for if it's exponential, you go to this second term and divide the first term. This is not even defined, so That's not even good. So you do this, the 4 divided by 1, you do the 9 divided by 4, and you do the 16 divided by 9. And you look to see, are these all the same? They're not. So that would be, it's not exponential. Okay, let's see exponential. Going up by 2, up by 2, up by 2, up by 2. Good. Now, 2 divided by 1. See, I already know it's not quadratic, linear, because this is going up 1, that's going up 2. They're not going up by the same. So now I'd go to the second strategy, which is 2 divided by 1, 4 divided by 2, 8 divided by 4, 16 divided by 8. And we all get 2. So this is going to be a exponential. Now in my, I believe my third period class, I actually messed up in class. I said r was equal to 2, but that's not true. Okay, r is not equal to 2. Actually, r is equal to the square root of 2, I believe. And I'll show you how to do that on these problems down here, which we learned last time. Okay, up 5, up 5, up 5, up 5. Good on the intervals. Okay, now I go to the second term. 40 divided by 80, that's a half. 20 divided by 40, that's a half. 10 divided by 20, a half. 5 divided by 10, a half. So when you go to the second term and divide the term behind it, you always get a half. So this is also exponential. Okay, now let's go ahead and do one of these word problems.
See, or just
okay. No, I was joking. I didn't have it paused. Okay, so these are these word problems, and you have to know these two formulas. This A of n. This is for the arithmetic, and this is basically just the point slope rearranged. So if it's arithmetic, we're using A's. If it's geometric, we're using G's. Okay, so basically, they give you two values. Okay. They give you two values. We're going to plug those two values into here. The A of n is your output, the n is the input. The AK is an output. Okay, let me change the color. So that's the output, that's the input. And then you're just left with n. If it's a geometric, that's an output, that's an input, and this is an output, that's an input. And then you have to solve for r. Okay, so let's read through this. And first thing I'm looking for is I'm trying to see if are they going to tell us it's arithmetic or geometric. So here we go, geometric. So we're using this formula right here. So we're going to do g of n equals g of k r to the n minus k. Now this one is they gave us two terms. So 43 people. This is a question about a rumor on day 3. So on day 3 there was 43 rumors, and then on day 6 there was 140. So on day 6 there was 140, and it's creased in geometric. So these are your outputs, these are your inputs. You always want to start with the further output to go into your g of n. Okay, or else you'll get a negative up here. So I'm going to do 140 equals, okay, the other output goes into g of k. That's 43. Then you have the r, which we don't know. Now the input for the 140 is going to go in for n, which was 6. And then the input for the 43 was 3. So now we have 140 equals 43 times r to the third. 6 minus 3 is 3. So now what you want to do is divide the 43. Divide 43. So now I'm going to flip these variables around. R cubed equals 140 over 43. And just leave this as a fraction. Now to undo a cube, you have to take the cube root. So to find r, well, r is going to be the cube root of 140 over 43. and I'll show you how to put this in your calculator. Once we put it in the calculator, I'm just going to kind of jump ahead while that's pulling up. Let's see. Once we Okay, so now what you want to do to put that in your calculator is just get rid of this stuff. Hit the math button, and then here number 4. Now, everybody kind of has different calculators, so you kind of have to figure your calculator out. So you're going to do 140 divided by 43. This is going to give us some crazy decimal. Okay, so now we're going to want to use this number later without rounding it, so I want to store it. So I want to store this. If you look at these letters, you have like the A here, the B here, the C here. Those are just letters you could store numbers in. You could use any one you want, but we're just going to use A. So that's color-coded with the alpha. So I'm going to hit STO. So it took this as your answer with an arrow. And if I do alpha A, it's going to put this number into A. So if I ever want to use it later down the line, I'll have it. So you could round it on paper to 3 decimals. It's just when you're doing your calculator work, you can't round it. So 1.482. 1.482, or you could have just left this. And now that we have the R, we're going to go back to the original, which is G of n. Now in this case, we could pick either of the points. We could pick that or this. But I'll use the one that we used for GK before and do the 43. Now this is going to be 1.482. This is what I mean by you could round, but I'm not going to actually use this. And then the n is going to be just n minus, okay, what was the input for 43? 3. So that's your equation. Now we could use this equation to find the rumors for any day we want. So they want the rumors on day 10, so we're doing G of 10, which is 43 times 1.482 times 10 minus 2. So that's 43 times 1.482 to the 8th power. Oh, I'm sorry, that should be a 3 here. My bad. So that should be 7th power. Okay, so now we're going to go back to our calculators and then just put this thing in our calculator. So let me just take a quick look. 43, open parentheses. Now, I want to use this thing right here. Like literally, if you have this calculator, you could just go up there and grab it. You don't have to do A. Or if you want to do A, you just do 43, alpha A. So I have this stored in A. Now caret is how you get a power. And then 10 minus 3, 7. And 675. So G of 10 equals 676. I think it said round to the nearest whole. Somebody told me that. But I don't know. So 676 is your answer. Okay. Now we're going to use the same type of strategy down here. This has to do with the number of seats in the rows. But what do they say? They say arithmetic. So you're going to be using A of n, which is an output, equals A of k, which is another output, plus d, which is the common difference, and then n minus k. So the same sort of idea here. I'm like, okay, the 5th row, that's going to be your input. There were 31 seats. The 11th row, there were 49 seats. So this is the term that's further along the line. That's farther. Okay, so we're going to put that output into 49. This ensures it's a positive number here. Okay, and then 49, what's my other output? It's 31. My goal is to find D, and once we get D, we'll go back to figure out what they want, the 25th row. Okay, what's the input for the 49? 49 was 11 minus the input for the 31. That was the 5th row. So now we have 49 equals 31 plus D times 6. Now, when we did this in class, a lot of students were dividing this 31 over, but since this is a plus, we should be subtracting it over. And then, of course, I do that. We subtract the 31 over. So 49 minus 31 is 18. This would be a no calculator, just to let you know. That's canceled. And I'm just gonna, it's d times 6, but I don't really like seeing it like that. I like it looking at like 6 times d. Since it's multiplication, we could change the order there. Now we divide by 6. Getting a little ahead of myself there. And I'm gonna flip flop them again. D equals 3. Now that we got our d, we're gonna go back to our original, which is a to the n. Keep this output clean, okay? Because this is the output we're gonna be looking for. Now since we use 31, we'll use 31 again. Now you put plus 3. Because that was my d, times n minus, now this k is going to be the input for this 31, which is 5. See, 5 is the input. Now you could distribute this 3 and make it look all pretty, but in this case we don't necessarily have to. We're trying to find a at 25. 31 plus 3, and you need to plug the 25 in here. Now orders of operation tells us to do parentheses first. Orders of operation tells us to do multiplication first. So this is 31 plus 60. So in row 25, there should be 91 seats. And I should put roomers here. Always put the context. If you don't put the context, you're giving them a chance to take credit off, even though you know what's going on. Okay, so now we're going to go into this linear. We've done linear before. We're doing quadratic. We're going to start studying these exponential curves. Okay, exponential. So, not sure. I know you probably learned this exponential before, but we're going to get better at it. Okay, so this form right here is similar to the thing we were doing with g's, because you're just getting used to the g's, and we flip over to x's and y's. G of k equals to the r n minus k. So that's what we're used to. So basically this is that. Okay, like this, this equation right here is the same thing as this. Okay, but like this n is your x, but see there's no k. So technically this is the output when the input's 0. So if the input was 0, you're getting a. That's why we call this the initial amount. Okay, B represents this R, which was what you had to multiply to get to the next term, which is called a common ratio. Now, exponentials are either going to go up or they're going to go down. Okay, because remember, you're multiplying by something. So if I was like 1 was 4, let's say R is 3. Now, let's use 2. If R was 2 and 1 is 4, then 2, then what happens is you're multiplying this 4 by 2 to get 8. Now 3, you're multiplying that 8 by 2 to get 16. Now you see these things growing? These are the y's getting bigger. Okay? But what about this case? What if R is like a half? And I'll do the same thing. Well, I'll start a little higher. So what if 1 was 16 and I said R was a half? So then 2 would be 16 times a half, which is the same thing, 16 divided by 2, so that'd be 8. And then 3 would be 8 times a half, which is 4. And 2 would be 4 times a half, which is 2. See how it's dropping? And then you have to be a little careful because this thing's not gonna cross through that x-axis because the x-axis is 0. See? Watch from 1 or it should be a 4. If this is 5, then that's 2 times a half, which is 1. This is 6, which is 1 times a half, which is a half. 7, it's 1 half times a half, which is a fourth. You see, these terms are getting smaller and smaller, but they'll never actually cross 0. So they're like nudging up to 0. Now, what makes that? This B is like your R. So if B is greater than 1, the thing's going to be growing. If B is less than 1, it's going to be dropping, decaying. Now they got the A, both positives here. Now if the A is a negative, it's going to flip over the, if you have a negative, so if you had something like 3 times 2 to the x, that would look like this. If you put a negative, if you recall from Unit 1, that flips it over, that reflects over the x. That reflects over x. That's the same thing as negative f of x that we did a long time ago. The negative's outside of the function. This is your function. This negative's outside of it. So it's going to reflect over there. So that graph would look something like that. So it can get a little more tricky, but not too bad. Now there is a lot of homework on this stuff, but it goes really fast. It goes really fast. So make sure you study this. It's either increasing or the graph is decreasing. Okay, this is concave up. It's going to be concave down. What they're saying is it's not going to do something like this. Well, I guess I have to be a little careful, but or sometimes it's concave up and then sometimes it's concave down. Concave up, it's not going to be like that. It's either always concave up or always concave down. Then you have the end behavior. The end behavior is either going to infinity. On this side, the end behavior is going to 0. On this side, it's going to infinity, and this side, it's going to 0. So there's really, the end behavior is only going to go to infinity. It could go to negative infinity if it flips, or it's going to be going to 0. Okay, if the form's like this. If you start adding stuff outside of this, then that's going to have, what I'm saying is, I didn't see it in the homework anywhere, but if I said like 3 times 2 to the x plus 2, now this is a vertical translation, so this whole graph would be going up 2. So then it wouldn't be 0, but I didn't see that, but you should be aware of that. Alright, let's see if there's anything else here. Okay, like I said, the homework is sort of long, but most of them are multiple choice, and they're pretty straightforward. Okay, so they give us a graph. I'm just going to call it f to make our life a little easier. So this is going to be the limit as x goes to negative infinity, and I just called it f, so I'll say f of x equals. So what we're basically saying is these x's are getting smaller, -1, -2. Where are these y's headed? Where are they headed? They're headed to 0. Okay, LIM. I think most of the people are starting to get this concept. The right, x is going to infinity, f of x. Okay, when that's the first x for 1. Here's the x for 2. Here's the x for 3. What's going on with these y's? They keep getting bigger and bigger, so that's going to infinity. Okay, this is some sort of reflection. It's actually, that's the reflection of this guy right here, so this just I mean, you don't have to know this right now, but this, an example of this would be something like -5 to the 1/2 to the x. That would be an example of that. It flips over the x. Okay, so left. LIM, x goes to negative infinity. LIM, doesn't look like an LIM. They didn't call it anything. Let's call this G. Okay, so as x is getting, these x's are getting smaller, these y's just keep getting smaller and smaller, so that's negative infinity. How about when x's are getting bigger? They're getting bigger. This line is approaching this x-axis, and the y of the x-axis is 0. Okay, so here on C, you have to know the form. Okay, so a is greater than 0, and this b is less than, it's between 0 and 1, so it's a fraction. So if the initial term is 5, then the next term is getting smaller because the next term is 2/3 of 5, and the next term is 2/3. So this graph would be looking like that. So LIM, x goes to negative infinity of g of x. That goes to infinity because these things are getting bigger. LIM, x goes to infinity of g of x. These dots, these y's are getting closer to 0. Okay, let's do concavity. Okay, so if you want to pause the video and do all 3 of these, if you weren't here, you could do it. Come back and pause at each one, but this is concave up. See, it looks like that part of a parabola, but it's not. So that's concave up. And it's decreasing. Decreasing means left to right. What are happening in these y's? They are decreasing. Okay, this out. You see how this almost looks like the right side of an upside down parabola? It's concave down. And these y's are getting smaller, so they're decreasing. Okay, 3, 4 to the x. Since this number is greater than 1, this thing's going to be growing. So this is going to be concave up because it looks like a smile. And these y's are they're always getting bigger. No time will the y's ever turn and start going smaller. Alright, so that should be enough to get you through. You don't have to do this example right here. We didn't do this one in class. I looked at the homework, there was nothing like it, so I'm not a big fan of that question. Okay, now, here are some rules that you guys have to remember. You have to be very, very, very comfortable with these rules. Okay, people tend to be okay at this one, but you all need to practice this and you need to practice this one. Okay, so if you look at these rules, they give you a few examples like x to the 5th times x to the 3rd, which is x to the 5 plus 3. Now nobody writes this because they just know it. When x and x, you have 8 x's. So they tend to just skip over. They skip over this part right here, and they just go from here to here. But the problem is, in this class, you're going to get something like, well, what's x to the? Well, let's make it a number. What if you had something like? I'll erase this stuff down. No, I'll do it here. What if I had something like 5x times 5 to the 3? So that would be 5. You can't add this because there's an x. I mean, you could add it, but you're not going to get like a real number. So it's like x plus 3. Okay? So a lot of times here, they're actually going to give you this. And you have to be good at this rule to work that way. So they're going to be saying something like this. What's 6 to the, x plus, let's say, 3? Or let's do a smaller number so we can end up figuring it out. Or we don't really have to. Let's say 2 to the x plus 4, something like that. And they're going to be like, hey, rearrange this thing. Rearrange this. And you're going to be like, okay, well, I know that's 2 to the x times 2 to the 4. But see, now you could figure this out. That's just 2 times 2 times 2 times 2. That's 16. So this is 2 to the x times 16. We generally don't like the variable or the coefficient on the right side, so we just flip it to 16 times 2 to the x. So now this looks like an exponential. So we went something that didn't, well, this is an exponential too, which you get this plus 4, but this gives you a different form of the same exact equation. And a matter of fact, this is actually kind of interesting too, and you probably never think about it, but what if I wrote it like this? 2 to the x minus a minus 4. Okay, and let's say this was it. That's all I wrote. So I'm going to relate this to the g stuff real quick. Now there's no number over here, but there's an invisible 1. So technically this would be the output when the k was negative 4. So this would be like the input, this would be the output. So if you put a negative 4 in here, you get 1, which makes sense, because 2 to the 16 times x to the negative 4, if you look at what we do for negatives, it goes to the bottom, it goes positive. So go to the bottom, it becomes 16 over 2 to the 4th, which is 16 over 16, which would be 1. So that's stuff you don't think about, but you can relate these exponentials with the geometric. All right, so that's how you work with this product. The power is if you take a number and you raise it to a power, and you raise that to a power, let's say 3, then this is going to be 4 to the 6th, because you have 4 squared times 4 squared times 4 squared, which is 2 4s, another 2 4s, another 2 4s, 4 is 6 4s. But you have to be good at this rule. Not necessarily this. You have to be good at the rule, because they're not going to put numbers in there. They're going to put letters. It's going to be like this. Oh, what's 2 to the x to the third? Oh, that's 2 to the 3x. And sometimes you have to work backwards and say, well, that's 2 to the 3 to the x. You see, it's a little tricky. It's really kind of tricky because they could say, oh, well, what is 2 to the 6x? Like, write this in a different way. Well, what they want you to do is break this down and say, oh, well, that's 2 to the 6th to a power. Well, 2 to the 6th is 32. Now all of a sudden I'm in exponential form. Remember, exponential form is a times b to the x. So in this case, there's a 1 over here. This is the initial term. So you're going from something that has a horizontal transformation into a vertical transformation. So let's look at these real quick. Like, for example, determine the horizontal transformation. So this is that whole stuff with the f of x plus or minus c, or the a f of x. This is from last quarter, plus c. Okay, and or like an f of bx. So if you look at this case, the original would be 4 of x. Now that might be hard to see, but the parent is always like the number with the power. Okay, so this is an exponential. They're both exponential. But how would this transform? Okay, so you could pause it and check it and see if you get the right answer. Okay, so in here you're putting an x plus 2, so this is a horizontal translation of negative 2. See how that works? This thing right here is the same thing as saying f of x plus 2. So all your x's would shift to the left too. Okay, now if you have 2 to the 3x, this is 2 to the 3x. Okay, they went on the horizontal transformation. So the transformation is being done on this because you're putting this 3x inside of that x. Okay, 3x is going to be a horizontal. I'm just going to round horizontal. This is dilation. And since this is inside of the x, it's going to go against your intuition. 1/3. Okay, here's another one. The original would be 9 to the x. Now you put x over 2 in there because you're putting x over 2 into that x. So this is also a horizontal dilation of 2 because it's x over 2. Goes against your intuition. X over 2 is the same thing as 1/2 times x. So you have to flip that and say, okay, all the x's will be multiplied by 2. Okay, this one's going to be, the original is 5x. You can pause it if you'd like. This is going to be a horizontal translation of, see, that's an x minus 1, so plus 1. Alright. So now they go on and say, you could use this product property. You could use this product property up here to turn a horizontal translation into a vertical dilation. Okay, so a horizontal shift is equivalent to a vertical dilate in these when it's written at these pluses. Okay, and they kind of go through an example. Well, we could do this example here. You're like, well, what are you talking about? Well, okay. You have 2 to the x plus 3. This is a horizontal translation of negative 3. Now let's use our rules. Well, since it's being added, I could break this down to 2 to the x times 2 to the 3. Okay, now 2 to 3 is 8. So this is 2 to the x times 8. Flip-flop these around, and you're left with 8 times 2 to the x. Okay, this is the initial term. So translating it to the left 3 is the same thing as vertical dilation of 8. Yeah, vertical dilation. And you see this is an exponential form. This, by the way, is your y-intercept. That's your starting value. And then everybody goes up by a multiple of 2. So it'd be like this: 0, 8, 1, 16, 2, 32. You see how it works? 364. You see I'm just going so fast because I just know it. Because if you put 0 in here, 2 to the 0 is 1. 1 times 8, 8. Put a 1 in there. 2 to the 1, 2. 2 times 8, 16. Alright. This one might be a little tricky. So this is 3 to the x minus 2. This is a horizontal dilation of plus 2. Now we're going to manipulate it. That's going to be 3 to the x times 3 to the, not plus 2, but the minus 2. So due to 3, to simplify this part, you want to use this property up here. If you have a negative in a power, it comes to the bottom and becomes a positive. Okay, whether it's a number or whether it's a variable. So this is going to be 3 to the x times, this is going to go to the bottom, 3 squared. So that's 3 to the x times 1 over 9. Now we don't like this number being on the right side, so this is going to be equal to 1/9 3 to the x, and that's your exponential. Okay, you should have an idea like how to graph these things pretty fast, because this thing here is your initial amount. That's your y-intercept. So let's call this 1. 1/9 is 1/9 of 1, so that would be your starting place. Okay, but at 1, okay, watch what happens. This 1/9 goes to 1/3. Not that big of a jump, because if you start at 1/9, the next term is going to be 1 times 3 higher, or sorry, 3 times higher. So you do 1/9 times 3 is 3 over 9, so your new term is 1 over 3rd. So this is the term for 1. Now you're going to do 1/3 times 3, because every term is going up by times 3. So when it's 2, you get 1. You see how it works? Now watch what starts happening. At 3, this 1 gets multiplied by 3, so it's 3. 2, 3. Now at 4, this 3 is getting multiplied by 3, so now you're at 9. You see how fast it's increasing now? So it goes real slow, shoots up real fast. So that'd be like the graph of that thing. You could look at this versus 3 to the x, or 3 to the x minus 2. There's a horizontal translation of plus 2 is equivalent to a vertical dilation of 1 over 9. Okay? I mean, I'm doing a little extra, but you know, I'm just showing you my thought process of how this stuff starts working. So now you have 4 times 3 to the x plus 2. So now they're writing this sort of like our g of x thing, right? So it's like 3 to the n minus a minus 2. So I forgot the 4. Sorry. So 4 times 3 to this mess. This would be like g to the k. So 4 is the output when the input's negative 2. So now we're kind of on the other side of the x-axis. We're over here at negative 2. You'd be at 4. And this thing's going to shoot up that way. Anyways, they just want you to manipulate it. So that'd be 4 times 3 to the x times 3 to the squared. And just to let you know, this is two different transformations. This is a vertical dilation of 4, and this plus 2 is a horizontal translation of -2. Once it gets manipulated, okay, this is going to be 4 times 3 to the x times 9. This 9 goes with that 4. That's 36 times 3 to the x. No more horizontal. There's no more horizontal translation. It's just a vertical dilation of 36 after you do all the work to it. So hopefully that'll be. Oh, is there more? Oh, yeah, there's more. Okay, so which is equivalent to this stuff? So they give you this 9 to the 2x. This is a horizontal dilation of a half. Now that's 9 to the 2x in case you can't see it that well. Now, I have to use that other property. If you raise something to a power, you multiply. Now they gave it to me like this, but I need to turn it into like this. Okay, so now I'm going to write 9 squared, and I'm going to raise that to the x because that's the form that I'm looking for. Remember, it's a b to the x, so I'm looking for this. All the problems I've did before. Look, any problem that I did before, I'm attacking this. If there's something here, that's whatever. If there's nothing here, then a is just 1. If there's something here, then there's something there. But this is what I need ultimately: something raised to an x. Okay, so this is going to be equal to 81x. So 81 to the power x would be 1 times 81 to the x. Every term's getting multiplied by 81. So it'd be like 1, 81, 2 is going to be 81 times 81. Term 2. Like that. Everybody's going up by a multiple of 81, so I'm not even going to try it. Okay, let's do this one. This one could be a little tricky because what happens here is when I first did this problem, I was like, okay, I need to manipulate this because they didn't give me a power. So it's like, well, let me make it into a power. So I was like, okay, well, 2 squared is 4. And then I raised it to the x. So I was like 9 times 2 to the 2x. And then I looked, and I didn't see it. Okay? I mean, I guess I could know it's not that one, but the answer wasn't there. So I was like, okay, well, let me attack this a different way. Let me start over here, and let me turn one of these into this thing. Okay, so let's start with C. So let's start with A. So that would be 3 times 16. Now this is what they wanted you to do. So x over 2 is the same thing as 1/2 times x. So they want you to pull the half inside the parentheses and leave the x out, because remember, it's a times b of x. So I'm looking for something to the power of x. So now I have something to the power of x. Now 16 to the half is 4. So anything raised to the half is the same thing as the square root. So x to the half is the same thing as the square root of x. So that's going to be 4 to the x. So does that give me that? No. So let's try the next one. 3 times, this is going to be 16 squared. See, I take the 16, I take the 2, put the 2 with the 16, and take the x. Now, is that equal to that? No. Okay, now I got a 9 times 16, same idea here, x over 2 is the same thing as 1/2 x. So what I do is I put the 1/2 with the 16, wrap parentheses around it, and put the x up there. And then you have to realize that anything raised to the 16th is just the square root of that number. So this is going to be 9 times 4 to the x, and they match. That's how you get that one. Okay? So some of the homework might be a little tricky for 2.4, but just give it your best shot. And then we're going to be a little ahead, which is going to give us more time to go back and review this stuff sort of the end. So, all right.